Alright, hello world. Um, Getting started on a brand new set today. We're in chapter 5, well, section 5 of chapter 1. Took a screenshot of this, so maybe I'll see if I can add it in the corner here real quick. Probably unreadable. Anyway, that's what I'm looking at today. Alright. So, yeah, I haven't looked at these yet. You can see there's a few more. It actually goes on until section 6 here. So there's about 10 problems. 60, they're all one giant problem, I guess. Number 60 has to do with Gaussian binomial coefficients, which I'm not really familiar with. Although I think they came up in some of my answers in the previous couple questions. So yeah, here goes. Q is a variable. Define the Gaussian binomial coefficient as in bracket k instead of parentheses. And this alone would have been, yeah, these are integers. Okay, so this alone is like a series. I mean, I suppose this is as well, but it's only powers, it's like even powers suddenly. Alright. K again has to be less than or equal to n, although it can't be 0. Oh, I see. N0 is defined as 1. K is not an integer. Then we just let it be 0. Okay. Suppose a Q avoids roots of unity. And sometimes we emphasize the Q. But not here in this first problem. Okay. And then the mention, well, reference to 10 is just the first time we brought up binomial coefficients at all. So back problem 10. Problem 10 is in an assembly of P people, select a committee of N members. How many different committees are possible? So that was probably the first time that we saw a combination. I mean, yeah, a combination. Alright, I guess I'm going to be writing like here, so maybe we'll move this. But yeah, that's what I'm looking at today for the first time. first one says to show that the limit as q goes to 1 of such a formula, oops, just gives you back the regular formula. Just a sec. Okay. I guess this definition is printed right there on your screen, but I'm not really familiar with it yet. So we start at n. Upstairs we decrease down to n minus k plus 1. And then upstairs we, or downstairs we take 1 minus q, q squared, etc. up to q to the k. And then we also have n0 is 1. And any k values outside of 0 to n, you just get 0. Well, so that part's true for this too. Like, this is clearly true if k is outside the normal range. If it's 0, we have a bit of a problem in the formula, so we're not even going to look at it, but we just get this. We get 1. Oh yeah, we get 1 in the regular case too, right? So it's true there. So it's true for all the boundary weird cases. Alright. So try to take the limit as q goes to 1. Alright, I have a bit of a problem there because, like, I can't... This first one is easy enough to count. I think that limit's going to be n. Well, because it's just q plus... I'm just noticing that, like... What is this, the case of k being 1? So, like, when k equals 1, you're getting this, which is this. This tends to n as q tends to 1. So I've noticed that. When you do look at k equals the next case, the q equals 2 case, or if you like, can we maybe do it by induction somehow? So what you do is you take this previous result and you're multiplying by one larger power downstairs and one smaller power upstairs. But I mean, I guess I don't love this. One of these is even for sure upstairs, but that doesn't really help us later on. Like if we have q to the 4 or q to the 6 or something, you know, I get every 6th q. I get 1 plus q to the 6 plus q to the 12, etc. as a sum. So I don't know if I can really keep doing this trick. And so, like, clearly this is supposed to go to n minus 1 over 2. We could, Yeah, we could use the previous result. I mean, I guess I'm allowed to use L'Hopital, right? So you can actually prove this real quick using L'Hopital. Right? So it's when you do attempt to plug in q equals 1, this is an indeterminate form, 0 for 0. And then you immediately get the previous result, but with n being... I guess you don't quite get the previous result, do you? I didn't notice that. Yeah, you don't. What do you get? You get n minus 1. Oh, do the q's cancel maybe? Yeah, because then you're able to plug in 1. So it's not the previous result, but you do get this right away. So in general, our terms, the ones that we're multiplying by when we go from one step to the next, you know, suppose you had just a random term in here like, let's say r plus 1 over 1 minus q to the r. When you use, so you can't plug in, well, when you try to plug in 1, for instance, you're getting an indeterminate form. If you do use L'Hopital, you're going to get, looks like r, right? And upstairs you get the same kind of thing, you get n minus r plus 1. But then you're able to plug in 1, and these cancel, well, you know, they just go to 1. So you are getting the sort of obvious thing that we need. As you go for 1. So I guess this is done by induction. That's 60.1. Like it's true for k equal 1. And of course we saw it's true for k equals 2. But whenever you're at a step, you know, your hypothesis here, suppose you're at n minus 1, or I should say r minus 1, when you multiply by the rth term, so like if for this we get this result, the formula for that is weird. It looks like I was going to do induction on k, obviously, right? Okay, let's keep going then. This is n minus r plus 1, right? So if you know that this happens as q goes to 1, I'm a little frustrated because we get an extra factor. Oh, it cancels. Good. Yeah. Okay, good. Then when you go to look at this guy, it's actually the same as the previous, but it's multiplied by... So our formula, when you stop at r minus 1, the denominator is, maybe I should write that down. This would be q to the n, down to, and downstairs you get 1 minus q, up to 1 minus q to the r minus 1, right? Upstairs, what do we say? It's like n minus k plus 1. So for us it's n minus, it's n minus r, right? We should be a little careful with that. I would think it was that. So I'm getting plus 2. Good, good, good. Yeah, that makes more sense. This is n minus r plus 2. Which makes sense because I'm about to multiply it by downstairs by 1 minus q to the r, and upstairs by the term that you get when you plug in r for k, so n minus r plus 1. So it's 1 fewer than the thing we just wrote down here. Yep, so far that makes sense. But what we know is from the hypothesis that this part goes to, this part tends to the previous result, n choose r minus 1. I'll just write it short in the short notation. And then this part we probably just talked about right here. That's the part we needed to go to this. So we know that that part goes to n minus r plus 1 over r. And when you do that, obviously this is n choose r. Alright, so 60.1 is not bad. I would say induction on k. It's pretty straightforward. Yeah, what happened there was you got an extra factor of r downstairs, so that turned this into an r factorial, and you got 1 fewer over here. This factor in the numerator cancels there, so you're getting, this part is still n factorial from here. That's still there. But this r minus 1 factorial has become an r factorial. And this term canceled and left you with 1 fewer. So you're actually getting this, which, these are the same thing. So that's it for 60.1. What is 60.2? Looks like, I can read it on the screen there. It just says, sure that it's symmetric in the usual way, but watch the case 0. Huh. Alright. Well, n0 we have said is 1, while nn, which he didn't make a comment on, is apparently the full, just plug in n's up here. So n minus n gives you 1 minus q. I mean, that's pretty straight, that's easy, right? You're getting the same series on the top and the bottom. I don't know why I would have to pay special attention to it. You can see that you're getting 1. You get 1 minus q to the n, all the way down to 1 minus q. But then downstairs you start at 1 minus q and you go all the way up to 1 minus q to the k, but k is n. So this is 1. So I'm not sure what... Pay special attention to it. Okay, well... what? Pay attention to the case k equals 0. Okay, whatever. Well, case of k equals 0 is very easy. The other cases, let's see. Is it obvious that this is symmetric? If you plug in n minus k instead, let's just use the definition. We'd get 1 minus... So upstairs we start at q to the n, we stop at q to the n minus k, and then downstairs you start at 1 minus q, you go up to 1 minus q to the k, but our k is again n minus k. It's a little annoying. So this is 1 minus q to the n. Remember, k is not 0 this time. This is decreasing, right? Yeah. So if k is, say, 1, you hit it here. Like, the second factor is the same as this, and they cancel. What about this 1 minus q. Probably, I imagine it doesn't cancel, right? Huh. It's a little weird. Anyway, I was just rewriting this to see what this is. So downstairs, the powers are going up. You know, the powers of q are increasing. Upstairs, the powers of q are decreasing down to this value, which seems to be k plus 1. Right? Yeah, k plus 1. And I'm supposed to notice that this is n choose k again. It doesn't look like n choose k to me. Although this is kind of funny because I know that this cancels. And these are getting smaller. They're not going to all cancel. So like if k was 1, for instance, you're seeing this guy doesn't cancel, but the next one does. The second one does. And this one does. So I can see that it's true for k equals 1, that the only thing that survives is this front matter. I don't think this is really an induction thing. I think this is just an observation. You know, I'm pretty sure if we're just careful with this, you can see that the stuff cancels and gives you the same formula that we started with. So if k is less than n, what can I say about k plus 1? I guess the other extreme is if you plugged in n minus 1, right? You're up right near n. If you plug in n minus 1, here you're getting n, which again just collapses. It gives you just this one term. And here you're getting that. So yeah, it's just clear by observation that for k equal to 1 or n minus 1 that you get the first easy case. Alright, I know k that is less than n, but I don't know really how big it is. Maybe it would help me to literally say, like, let d be n minus k or something. So I have some, because when it's 1, all you get is the one term, and that's kind of silly. But otherwise, we should be able to subtract, like, we know that there's a point upstairs where you get to d. Right? And then if you keep going, we're supposed to keep going until you get k plus 1. So what about a case like, 10 and 3 or something? you can see that you're supposed to stop at, in this new form, you're supposed to stop at 4, 1 minus q to the 4. But this difference is 7. So we would keep going, yeah. So in general, you keep going for the larger cases. And we stop at 1 minus q to the k plus 1. So that's the way the numerator looks in our new formula. Downstairs, we stop at this d value. But we also have all the lesser values. Okay, we're starting to get some cancellation, right? Like you can see these cancel. 1 minus q to the d minus 2, 1 minus q to the d minus 1. We stop here. So those cancel. Everything, all of this cancels. Unless what? Unless k plus 1 is like, but we already covered the case of k being 0, so never mind. So all this cancels down to some point. The first one that cancels is 1 minus q to the k plus 1, whatever that is. So in the case of, say, k being 3, you stop at, the first thing that cancels is 1 minus q to the 4. Which means we're left with we're left with 1 minus q to the n, yada yada, the usual. It's a descending factorial like, factors. But the last one that you'll see for sure is this guy, 1 minus q to the d minus 1. Oh, plus 1 is what I meant to say, right? Plus 1 is there. That's the last one you see. And you can see when we solve for that, d plus 1 is what you get in the numerator, in the correct formula, in the original formula. So it's working out. I knew, yeah, it's not really induction. This is just like bookkeeping. Let's call it bookkeeping. It's just some algebra. It's like clearly working out. And then the last one you see downstairs is 1 minus q to the k, which, well, what do you know? What a surprise. So that was an easy problem too. 1 minus q squared, up to 1 minus q to the, we noticed that this is the first one that cancels, k plus 1. So it means the last one that did not cancel is 1 minus q to the k. And what a big surprise, this is the formula for n choose k. I'm calling it choose, but I mean obviously the Gaussian binomial coefficient thing. I don't have a name for that. Anyway, that's 60.2. I don't know why we had to pay attention to the case of k equals 0. That was an easy case. But all right, that's point 2. Prove the identity. Prove the following in x. It looks like it says the product of, 1 to n of 1 plus q. Let me just make sure I'm writing it. 1 plus q to the k minus 1 x. As k goes from 1 to n. Show that this is the same as the sum of these Gaussian coefficients, q to the k minus 1 over 2. So what's that? The sum of, the first k terms times x to the k. K goes from 0 to n. Okay. That's interesting. All right, so I know that it's symmetric now, and I know that the limit, I don't think that's really going to help me. I'm just remembering the two results we just showed. Shouldn't this feel familiar? Like, is this like a binomial? letting this change. So what is this like? This is strange. That's interesting. But yeah, does it remind us of the binomial theorem? We wouldn't usually have, yeah, we would, but this wouldn't be changing. Huh. I'm just remembering like the usual statement would be what? I guess something like the product of from 1 to n is obviously this, and we'd have a formula like this. Q to the k, x to the k. K goes from 0 to n. So that would be the usual binomial theorem. What if you do this with it? I can't change it. If you do that with it, it changes. Yeah, it changes the whole nature. So this is really interesting. I wonder if this is why he made it, so that you could alter these coefficients inside these factors. You know what I'm saying? Because in the usual one, if you put powers of q here that change, I can't use the formula anymore. Anyway, whatever. It reminds me of this. It clearly has an analog. I don't see that helping us. Well, so one thing that is happening is these numbers are changing. Like if we take q, if you sum these up, let's see, I don't mean sum, I mean if you took the product of qr from like 0 or even 1 to k, you should get this back, right? Something like that. I'm just adding 1 plus 2 plus 3 all the way up to k. Although it's strange that, no, it's not strange at all. So you can start at 0, you can start at 1, it's immaterial, right? Because you're just getting 1. So I guess this could come in handy, right? I mean, this just explains the last term. Well, no, it should explain every term. It should explain every, like, the kth. So of course it explains the case of n, of k equal to n, but it shows up in the formula, which means this product shows up in the formula. Alright, what else does this look like? When you plug in 1, you get nothing, right? So you get, so our left-hand side looks like 1 plus x times 1 plus, this thing again. Wait a minute. Now it's going up, right? Okay, so qx, 1 plus q squared x, all the way up to 1 plus q to the n minus 1 x. So we've been playing with this last, almost. Oh, sorry. Here. Did it with negatives. This was the first time I had introduced, I've seen that form, right? I don't think we did it prior to that. We did talk about binomial coefficients a while ago. So we did this same form but with negatives instead of sums. And then here's the sums, but it was sort of a more general case, right? Because you're including reciprocals. So I had looked at this case in particular, I guess. When I did 52, I did it slightly differently than he did it. But anyway, you can see that, oh, these are odds. These are just the odd ones. right. Huh. So I guess we haven't seen this exact form, but we played with similar stuff. It doesn't really, these are kind of special cases of this one. Huh. So yeah, stuff like this came up recently, but like this function came up recently, but not exactly this form, but pretty close. What's the next one? Ew. So that's not quite as nice as the usual binomial, what's it called? Pascal's identity. That's clearly the analog for these new coefficients. This is Pascal's identity, but with Gaussian binomial coefficients. Sure, that thing which we have defined as a rational is in fact a polynomial of this degree. Yeah, well, okay, sure. Show that it divides, right? Show that the denominator actually divides out. Huh. Well, I started to notice that that's probably true because, like, when you look at that was like the first thing I said was this is a series, and you can keep doing that, but it's harder for me to explain like where it stops. So like when you do the second factor, you get powers of 2. You get q squared, q to the 4, q to the 6. But you do get a sum, but it stops one fewer than this. And then for the third one, you get 1 plus q cubed plus q to the 6, etc. For the third factor, you know, the 1 minus q to the n minus 2 over 1 minus q cubed. So again, we're going to stop at like q to the n minus 2, but you're using powers of, you're getting multiples of q, of 3 for that third factor. So in general, like for the rth factor, you're getting 1 plus q to the r plus q to the 2r plus q to the 3r. But you only get a finite list. It stops, in that case, it stops at n minus r plus 1 upstairs. So I guess I'm wondering if you could do it that way. Which again is sort of direct observation. It's not, but maybe this would be easier with induction on that particular problem. Anyway, clearly I'm getting ahead of myself because I haven't thought about this one yet. So here's our left-hand side. I should be able to just look at the coefficient of x to the k, right? I should be able to say that you expand this, you get some series, we don't know what it is. You can clearly there's a 1 out front. That must be the n0 case. Oh yeah, q to the 0, sure. So, we're seeing that we get 1 plus yada yada, and then there's a term that I need to figure out for x to the k. And there's a coefficient here that I need to generalize and then show that it's this. And then the last term, of course, is q1. That's like q to the power of 0 plus 1 plus 2, all the way up to... So the last one we can see is q to the... is it n times n minus 2? I guess it's supposed to be this. I'll just write this down and verify it in a moment. This is the last term that we would get, right? Is it always the way it is? You stop at n minus 1. Oh yeah, I guess that makes sense. So like if you added up 1 plus 2 plus all the way up to 10, say, you usually do, I do it 10 plus 1 times 10 over 2. Oh yeah, that's the same formula. Okay, so yeah, this. I wasn't sure if I was off by 1. Right. wait a minute. No, yeah, that's the same formula. Yeah, good, 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 good. There's n minus 1 plus 1 right there. Good, good. I was going to say, I always get this, not the other way around, but that's because I'm stopping at n. If you sum to n, you get this formula. All right, anyway. So yeah, I need to... So evidently we get this, you know. What's sitting here is... What's sitting here is supposed to be our n choose k, the new formula, with the q to the, you know, the sum. We have to explain why that happens. So what else is this thing? I mean, I have to include all. Well, you don't have to include when you multiply these factors. You're either some of the time you include one, some of the time you include the business end of the two terms, right? Every time you have a power of k, you've included k of the business end, and I want to say n minus k. Does that make sense? Because there's n factors. N minus k ones. So in order to get a power of k factors of x, because there was only one factor of x in each of these factors, right? If you have this, that means you have q to the power, the sum of, here, let's explain it more slowly. You have k, I should say factors. You have k factors of the form q to the something x, right? In order to get x to the k, it has to look like this, where the r comes from, you know, r goes from 0, 1, all the way up to n minus 1. You have k of those factors, and obviously the rest are 1s, and n minus k factors of 1. That's just what happens when you multiply these things together. So you're either, does that make sense? So you've already got this combinatorial thing happening where you're like, well, which ones am I going to take? You have to take all of them and collect them together, and that's how you get this. That's what you get here. That's what this coefficient would be. So now I just need to address, like, how many ways can you select k factors of q to the r, you know, from this list? And how many ways? Well, is that exactly what you mean? I don't care about in how many ways. That's not what I'm saying. I want you to sum them. Like, let's do an example. If you're looking at, like, x to the 3, the coefficient for that, one way that could happen is you just grab the first 3. So it could be like 1 plus q squared. Or it could be 1 plus q cubed. Or it could be, you get the idea. And you have to go through, like, every possible combination. So it could be 1 plus q squared plus q cubed. Q plus q squared plus q cubed. All the way up to the final 3, you know, q to the n minus 3, q to the n minus 2, q to the n minus 1. There's all these different ways. So, oh, yeah, no, that's right. Is that what I meant? I meant multiplying. You fool. Sorry, sorry. These are products. These are products. Silly. Um, yeah, so it's not so much that I care about how many different ways you can do that. It's that I care what the sum is. Oh, hey, Mr. Kalman filter. That's how the generating function. Yeah. Right. Hmm. Counts and versions. Yeah, I don't know what you mean. I know what I follow your first comment, but um, hmm. This many sums. Hmm. Guess what's kind of bugging me is I don't really get the full sum at any point, right? Hmm. Yeah, thanks for popping in, Mr. Kalman filter. Um, well, okay. I mean, I guess what's a little weird is you'll always get something here. So it's not like this just pops out. Um, you're getting pieces of this, right? Like you'll get q cubed. That's the smallest thing you'll get. Um, and of course, you will have this as a fact. Well, I don't know that it's a factor. Um, but this will be contained in there. Evidently, it's a factor, but I don't really see that. But like, we got q cubed, q to the 4, q to the 5. So like, we've almost got the full sum, but that's kind of the wrong way to think about it anyway. So what is this again? Upstairs, you start here and you go down. Like that. And then downstairs you go up. So it's this many sums of q, is what I'm supposed to get as the general coefficient. Paths on a lattice of size n by k. Oh, that's interesting. Huh. You know what? That's probably like, yeah, you're right about that. He talks about that in a later problem. I think he's going to talk about that. He says the number of zigzag patterns, here it is, street corners. He's talking about lattice points. So that's like 60.8. Sorry, you can't really see it. And he's even, blah, blah, blah. Consider a plane. Is this a new problem? That's 60.8. Yeah, I think this is a new problem, so never mind that. So yeah, on the next page, he'll talk about lattice points and like shortest paths and yada yada, networks with streets. So yeah, that's coming up. I'm not going to get to it today, but probably next week I'll be tackling those three. Oh yeah, here's your inversion. Yeah, I haven't seen this stuff before. I also don't remember Catalan numbers. I don't know if I'm familiar with Catalan numbers. It's a number theory thing? Or I guess it must be a more like a general combinatorics thing. Right, combinatorics, yeah. I've definitely heard of Catalan numbers. I don't think I've ever... Oh, yeah, I'm not really... Yeah, you could say I have no idea. I've seen the Wikipedia page for Catalan numbers. I've never actually found a bijection from left to right that gives the proof. Okay, yeah. That makes sense. I had one class in combinatorics, like 20, maybe 22 years ago. And I had a course in algebraic geometry, but that was a couple years later. But a lot of this early stuff in this book is... So like the first section is on series and sequences. And I mean, the first section was combinatorial, like sort of obviously combinatorial. But then, yeah, second section is obviously still combinatorics. So yeah, we're doing a lot of combinatorics early on. It's not going to stay that way though. So where are we? We're in chapter 2 already? No, we're not in chapter 2 yet. So yeah, chapter 1 seems to be a lot of combinatorics. Chapter 2 is transformation of series. And then blah, blah, blah. And then chapter 3 you just saw was real sequences and series. So it's going to get away from combinatorics at some point, but early on, I'm supposed to be learning it. I wonder what he has to say. So 60.1 was obvious, 2 is obvious, 3 is the one we're looking at now. Sorry, you can't see it. There it is. Yeah, I think he's basically saying what you just said. Well, making a bijection. And proceed as in 50, 51, 52. Okay. 50, 51, and 52 are the, he gave us, yeah, there you go. He gave us like either he gave us basically a functional equation and then said, find the power series that, find the coefficients for the power series that represents this function. So yeah, very much generating function stuff. But yeah, his answer for 60.3, which is better than what I am trying to do. I was getting nowhere, I guess. At this point, I was going to be like, I don't know how to count these. Anyway, but he noticed a functional equation. And then just did the usual thing. That's obviously the right way to do it. So I'm going to think about this some more, but the actual answer is to observe this 1 plus x f of q is f of x times 1 plus q to the n. Yeah, if you don't want to cheat, find this functional equation on your own, and then you'll get the answer. Once you find that, it's from there, it's probably not too bad. I think that's basically what you described, right? But you would have to first know this functional equation. Oh yeah, okay, fair enough. Yeah, you should. Yeah, the only way I know how to do it is this, but I wouldn't have thought of this. Like, now that he said this, I'm going to be able to solve it. But if he hadn't said that, I would still be here like, how do I count all these paths? So I'm going to stare at that for a second before I actually do it the proper way. So like it's clear for x, like if k is 1, you are going to get just this coefficient. That I can see. And by symmetry, it must be the same for n minus 1. If you used all but one of these, like say you don't use this term, but you use every other term, you'll get a sum of x to the n minus 1. But the q's, that's weird, right? You'll get this. Well, no, one way that you get it would be this minus 2. So it must be, all right, let's try that again. For the k equal 1 case, it's kind of obvious. For the k equals n minus 1 case. Oh, no, yeah, you're fine. If it's n, it uses everybody, and then you just get 1. So that must have been the case that was obvious to me. I see, okay. So when k is 0, that's also obvious. And it's true, you get 1 here. You get q to the 0. So I don't know if I said that, but those are the easy cases, right? In the case of k equal to 1, it's like you're just choosing which term you want, and your sum of all those is this. That part's obvious. If you're going the other way, n minus 1, you're picking one of these powers of q to not include, and you're doing that for every power. So it's like you're summing up. I don't know why I'm thinking about this, but if you're in the case of like k equal to n minus 1, it's like you're getting your full sum. Let's say you're letting r go from 0 to n, and you get your full sum minus q to the r. So it's like n plus 1 of these minus 1 of them. It's just this, isn't it? But I wasn't expecting n for this value. Right? What is n1? It should be... The limit is n. But isn't this the... let's see. So this part is that. Wait, yeah, where's the n come from? Huh. Oh, not k. I meant n here. I meant n. In any case, I'm only looking at the easy cases. I have no idea how I would handle this without his answer. I guess I wouldn't. Yeah, that's right. That's right. Yeah, it's 60.3 there. Right here. But yes. Yeah, what you said is correct. Yeah, I think I have it on the screen there on the bottom. Or up here. I also wrote it right here, but you probably can't read my scribbles. It sounds like if you've done algebraic combinatorics, then you've probably already done this problem. You've probably already seen it. This is sort of fundamentals. It's not like tricky stuff really. It's I'm just not familiar with these at all. But if you've done like any more advanced combinatorics, you've probably seen this stuff. But this was the first time I've even seen this function. So yeah, this is f, and we're supposed to notice that it satisfies this and then do the series. That's the like nice way to do it. I haven't thought about that. It's probably pretty straightforward. It looks pretty straightforward. Like if you put a Q here, yeah, I probably should have noticed that this is recursive, but I was just trying to do it by brute force, as always. Yeah, what happened to my n-1 case? I'm a little confused. The one case I think I get. The n-1 case should just be sort of the complement, right? If we had everything except the first one, say, that's just the sum minus 1. So you're just summing up the sum. I just wrote it right here. The sum n-1 times, right? Why is that n-1? Why wouldn't it be n? Common filter says oh, I see. Do you mean, like over 2? No, it doesn't make sense either. You meant... Huh. I mean, you could do that. You could do this and then multiply again. Right? Kind of weird. Yeah, I see what you're saying. Yeah, I was getting n plus 1 here, not n. So... Oh, that's why I got n at the end when I subtracted. I see. Minus the sum. Yep, minus the sum. So I'm getting this for the n-1 case. How is this n again? It's only n if q is 1. Right. Yeah, that was my first observation. Is this is an analog of the binomial theorem. Does that mean I can prove the binomial theorem with this recursion as well? This right-hand side is just a power series. So if I had, 1 plus qx to the n as my function, what happens if you plug in q? No, it's no good. There's got to be some sort of recursive. What's with this power? I guess it doesn't have to be some sort of recursive relation. Okay. What if I... Yeah, okay. I could fidget with the n value, but that's not really the point. Yeah, there's something obvious there. Like, binomial is a generating function for something. Oh, yeah, how do you do it the normal way? Like the way he said it basically in the book. So once you get this relation, which seems like it's probably pretty obvious, this times the next term would give you, if you plug in q here, if you plug in q here, it scales it up, so you get that last term, but you're missing the first term, and here's that missing first term, the case of k equal 1. So it's kind of obvious that this is true. Anyway, now that you know that that's true, just assume that your function satisfies, some power series, and then write this down again using your assumption. So if f equals this, then the left-hand side is the sum of an q to the n, x to the n, and on the right-hand side we have the original series times 1 plus q and x. This is just a product. So this is going to scale our coefficients by like q to the n, like we're going to, well, I'll just keep going. On the left, we get, I'll just do it kind of slowly. You can probably do this in your head at this point. Yeah. So you're just going to equate the coefficients on both sides for a particular, like for x to the k, and you'll be done. You'll probably get this formula or something. Yeah, so on the left you get q to the n, x to the n, and then it shifts by 1. I guess I'll just keep writing an q to the n, but it shifts by 1. And then on the right, we're getting just the original series. And then we scale it by q to the n, but we also increase the exponent by 1. And anyway, just group these and what the? All right, cool. Good to see you, Kalman Filter. Thanks for the help. I'm not familiar with your method, but I'm sure you're right. This is probably like some fundamental stuff from algebraic combinatorics. in any case, it's got to be better than staring at this and wondering how to count them. But also, yeah, your comment that it relates to lattice points, like paths on a lattice, is pretty on point. It's like exactly what's going to come up in the next page is him talking about zigzag paths and stuff. So that's all related. I don't know why this fell apart on me. It's about to just say something trivial. It's supposed to tell me, well, how did I get the same statement on both sides? This can't be... Oh, I don't have the same statement. I'm missing a Q here. Good. So, wait, isn't this the same? Q to the n, x to the n plus 1. Here we get q to the n, x to the n plus 1. Okay, I mean, I guess that's a good thing. So, but... This doesn't sound right. I'm supposed to get this formula for the ANs. Alright, now, let's... First of all, this is true. What I wrote down is correct. I got it from him, so that's why we know it's correct. But also, it's kind of obvious. When you plug in qx, you lose the first factor, but you gain a factor of n plus 1, basically. So you multiply by the first factor, and then you'll get all the stuff that you see on the right-hand side here. So this is clearly true just from observation. So if we let it be a power series, as k goes from, I don't know why I wrote n, but let's say we let k go from 0 to n. Well, whatever, I shouldn't have done that. Let's say n goes from 0 to capital N. In any case, here I am applying it to this formula, so I plug in qx instead of x. So we're going to get q to the n, x to the n. Here we get q to the n with an extra x. That's the left-hand side. On the right-hand side, you get the original, so no q's involved. But we should now just be able to say, like, ak q to the k equals ak. This doesn't make any sense. That's not the right formula. Like, right? It doesn't even make sense. And on the right, I got q to the n. Oh, you dick. I see what I did. Okay, sure. This is what I get for being sloppy. Alright, let's try again. So this is the actual answer. Like, we started with a function. This is what I get for using all the same index, right? You can't just make all the indices n. It gets a little confusing at some point when you multiply by the same index. Like, yeah. Anyway, this is our function. We're supposed to show that it's equal to... And it's funny, when it's phrased like this, I probably would get it correct. I don't know why I didn't think of this immediately. If you just phrase it like that, like now that I recognize this is a power series. Anyway, let's call these, effectively these are AK. So show that that happens for this function. So notice that if you were to plug in qx instead of x, it sort of scales this up. You're missing the 1 plus x factor that came first, but you're gaining an n plus 1 factor. Like, well, you're gaining a term where k equals n plus 1. You're gaining 1 plus q to the to the n instead of 1 plus q to the n minus 1. So on the right hand side, what that does to your function is it includes this extra term that you didn't used to have, an n there. There's nothing really wrong with what I just wrote there, but just be careful with your indexing when you go to do the power series. So now we're going to assume that your function is given by this formula, right? And then just do it, like use this relation on your function and you should have the answer. So if we do this nice and slowly, you'll get, so you have the sum of ak, as k goes from 0 to n, and then instead of x to the k, we actually have q to the k, x to the k. And then on the right hand side we have the original function, but it's times 1 plus q to the n, okay, not q to the k. Maybe don't use the same index and you won't get confused like I did. Anyway, so this q to the n is introduced in each coefficient, but this scales up. No perpetual motion machines yet. That'd be cool. That's why I got into this business. Actually, I think I wanted to make phasers. And, oh, really? I don't think, that doesn't sound like it would work without a battery. I guess you could do, I guess if you made it super efficient, you could maybe make one that like very, very, very slowly decays. I don't know though. I'm not an engineer. Well, they should be very, very rich then, right? I guess it doesn't mean it scales just because you can make something. I suppose that's true. You would need like a magnet the size of the sun or something. But I don't know. What am I doing here? So if we do this super slow, I don't have to do it that slowly, but we'll go ahead and take our time with this. Here's our left-hand side. This changes. It's q to the k, x to the k plus 1. But we usually scale this back. So like the left-hand side now says ak q to the k, and then here it says ak minus 1 q to the k minus 1. That's the coefficient of x to the k. That's on the left. And on the right we have just itself, and then we have an extra q to the n, and then it gets scaled. So you have ak q to the n floating around, but then it got scaled by 1, it got shifted by 1. So when you write it in the new form, it's going to be like ak plus q to the n ak minus 1, that's all. So we're equating these finally. We just say, we're just trying to solve for ak, and we know this is true. So now we've got that like recursive relation between the coefficients as well. So we started with a functional equation, or like a recursive relationship between the function and itself, and that translates to, if you assume it's a power series, that translates to a recursive relation on the coefficients. So we're looking at ak q to the k plus ak minus 1 q to the k minus 1 equals this junk. That's an n, not a k, right there. Anyway, whatever, just subtract them and start solving. We could, I don't know, subtract this one. So you're looking at ak times q to the k minus 1 is equal to q to the n minus q to the k minus 1. Anyway, we kind of want to iterate this maybe bring it back down to 0. Do we know what 0 is? Like if you let k be 0 in this function, say, well, okay, it doesn't make sense in this function, but if you look at the k equals 0 case, you're looking at just the constants, so of course that's 1, so we know that a0 is 1. That also makes sense here. It's by the formula, you know, like you're seeing 1 times 1. So no, it doesn't break anything when you notice this. Good to see you, Jamie. Hey, self-winding watches don't count either. They've also got motion. That's cheating. Although that would be, yeah, that doesn't count. That doesn't help anybody. Although that's pretty complex. Maybe I should work on watches. All right. Sorry, getting distracted by voicemails. Yeah, what were you going to do with this? Usually, so of course we're going to divide by this q to the k minus 1. I just want a formula in general for the AKs, and we're going to show that it is this. But in order to do that, we're going to have to start at 1 and sort of iterate. So, you know, do you have a formula for AK minus 1? Like, right, we'll just do it the simple way. We'll sort of explain it, right? Like, now that we know this is 1, we can just let k be 1 and see what you get. So we're going to get, you know, this is 1 times, and then the formula is this q to the n minus 1, apparently, right? We're doing the k equals 1 case now. So here you get q to the 0. I'll just put a 1 there, okay? Because k equals 1 in this case. And then downstairs you also get q minus 1. And then, so you're gonna be seeing that this obviously works. It's the previous, and then you get q to the n minus q. Downstairs you get this guy, q to the k again. But this time k is 2. Okay, that's right. Does it probably look backwards because we usually negate these. Anyway, yeah, we negate both. So you wouldn't usually write it this way. You can write it the other way around if you want. 1 minus q to the n, 1 minus q. Same thing. And then down here, you know, it's a1 times q. It's annoying. Oh, you're factoring a q out. You see that? Yep. So the numerator is going to decrease by 1, which is what we wanted to happen. And then the denominator we're going to leave alone. The denominator already looks perfect. But apparently you're going to factor a q out. So like this a2 is the first time that you see a q. So here we have like a q to the 0. In this case, we have a q to the 1 floating around. We get q a1 times 1 minus q to the n minus 1, which is what we wanted. We want the top to decrease in power, and we want the bottom to increase in power. So you're sort of observing that it's happening. So in general, should we do one more before I try to generalize? If you look at A3, you're, so here's A2. We're going to put that here. Well, I'll just write A2. And then we'll get our formula of q to the 2 this time, minus q to the n. And then downstairs we get 1 minus q to the 3, like that. But anyway, that's the same as, and we're going to factor q squared out, right? So it's the same as q cubed times a1 times 1 minus q to the n minus 2, 1 minus q to the n minus 1, and then downstairs you get a 3 and a 2. Yep, a 3 and a 2. I'm scrunching this up because I don't care that much. We need to like generalize it. So in general, from our formula here, we're going to get q to the k. Well, wait a minute. Huh. Guess that wasn't what I was expecting, huh? I don't see why not. This was q. It ends up here. And then you get another q squared, so why wouldn't it just be q cubed? It is. It's the sum. Huh. I'm going to keep going, but something's fishy about this, right? Anyway, in general, here's the first one, right? You have a 1 minus q coming from the very first term. You get q squared from the second term, q cubed from the third term, etc. So downstairs we get 1 minus q, 1 minus q squared, all the way up to, and if you stop at k, you'll have 1 minus q to the k as the final denominator factor. And then upstairs, of course, we've got, so we started with 1 minus q to the n. The second one you have 1 minus q to the n minus 1, so and the last one you end up with is q to the n minus, it's not actually k, but it's one fewer than k. So it's 1 minus q to the n minus k plus 1, like that. And obviously that is our familiar formula that you're seeing right there at the top. But what's funny to me, I must have made a mistake, right? Because we got that part, but I didn't get the correct power for q. Am I missing something? Q to k minus 1. And here I subtracted this guy. So that's correct. This equation's right. A0 is of course 1. Change this order. So here's q to the 0 out front in a sense. Oh, no, I am wrong. It's not q to the k. Wait a minute. Yeah. This was silly. Hold on. Here you have a q, and then you have q to the 1 plus 2, which is 3. On the next step, yeah. That's funny. You see what I did? I observed that it went from 1 to, like, from 1 to 3 is what it did. You see that? It's q to the 1. Yeah. Well, yeah, there was no 1 in A1's formula. It went from 1 to 3, and for some reason I was like, oh, that's okay. But this is wrong. That's not what I meant to say. It's 1 plus 2 plus 3. That's funny. So for k equals 3, you happen to get, so for like 2, you get 2 times 1 over 2, which is 1. That's correct. But for 3, you get 3 times 2 over 2, which is 3. I noticed that the sum of 1 plus 2 happens to be 3, and that was like the third sum, and I was like, oh, it must be a k, but that is not what I meant. This is actually the sum of these things. So if we did it one more time, a4, you would get q to the 4 times the previous stuff, you know? Yeah, that's all. So on 4, you're supposed to get 7. You're not going to get 4. I meant to write the sum like this. It's all right. It checks out. That's 60.3. That's how you do it. I definitely got stuck. I don't think there's really a way out to do it my other way. Well, no, yeah, you'd need to. It's like if you were good at combinatorics, but then you would just use a generating function, and that's kind of what we did. But yeah, still, if I had to like do this, if you gave me this problem initially, like find all the sums of all the combinations that you can make of powers of q, I would have no idea how to do that. But the appropriate way to do it would be to set up this product and then do what we just did. You know, you'd have to recognize that these are coming from this product, which is really actually pretty similar to the stuff that we did early in the book, like we did in the first couple pages. Like back then he was talking about making change, and like in how many ways can you arrange stamps, and how many ways can you like and how many ways can you compose 78 grams using just these weights. And in every one of those, he would mention an equation like this, and he would have us set up a sum like this, and then solve for the coefficients. So what we were doing was creating generating functions, and then using the coefficient to get an answer. So if you did encounter some nightmare question like this, where you have to count all the ways, like you need to sum the coefficients where the terms are a combination of different powers, you would need to kind of recognize that they're coming from terms like this: 1 plus 1 of the powers times 1 plus 1 of the powers times etc. And then you'd be like, all right, that's the set I'm choosing from. Let's make a function out of it, find a recursive relation, and then use that to solve the coefficient of the generating function that you just made. Anyway, I'm rambling. I'm going to have to call it a day there. I'm glad we actually, and this took a while for such easy questions. It's kind of funny. But yeah, that last one, I definitely needed to see the answer. I wouldn't have, for some reason I wasn't thinking of the left-hand side. I wasn't thinking of the right-hand side as a power series. If I'd thought, hey, this is a power series, then there's a chance that I would have been like, oh, this is a function. Like, this is the function. Find a functional equation for this function on the left, and boom. Then it's the same as the stuff we were just doing last week. Anyway, I'm going to move on. As you can see, we got some exciting stuff coming up. 60.4, I noticed, was like basically Pascal's identity. Maybe we can call this Gauss's identity, except that I'm sure that's already a thing. 60.5, show that as a polynomial. That one's going to be over my head, I'm sure. Even though I thought I saw that it was happening, but yeah, I'll have to think about this one to really understand it. 60.4 I don't know how to do off the top of my head, but But it seems like that's like another fundamental one. You know, in the regular binomial coefficient case, that's pretty straightforward to show. It's actually kind of obvious. He has us prove it 3 different ways earlier. But this one, I don't know. I haven't thought about it. 60.5 is one that requires some algebra, I'm sure, that I'm like not familiar with. And then 60.6, according to our notation with q squared, sure, prove that this identity is true, where you have q squareds here. Oh no. This might be one that we already did. Oh, it's similar. What the h's remind me of a problem we did. Oh, it was differentiation, wasn't it? Oh, no, it wasn't. Where were these minus h's coming from? That was a while ago, apparently. No. Couldn't be this far back. No, it's not this far back. Okay. Back up. We must have just done it. I thought it... Wasn't it like this? There it is, there it is, there it is. 35. It reminds me of this, where like we took it's like a generalized factorial. I don't know if this has a name, but so instead of decreasing by 1, you just decrease by h, but then it happens to have the same, like you can use the binomial theorem to prove this result. And there's a multinomial version. Anyway, that's what this extra h kind of reminds me of. I don't think that's the answer. I don't think that has anything really to do with it, but I'm just noticing. Also, one of my answers last week, like on maybe 50, one of these, 57, 58, one of these guys. Oh, there it is, q squared. I don't know. One of them had like powers of q, and I got an answer that made no sense to me, but it was definitely expressible. It was like this. It was like I got an identity. Oh, maybe it's the same question. Look at that. There it is. We got z and z to the minus 1, and that's probably similar to 52. The one where he had like z, he has odd powers, but half of them are reciprocals and half of them are regular. And he had us show that, he had us find the coefficients if you expand it in like a Laurent series. And I got a formula for it, doing it my way, but I didn't know what to do with it. It's probably this formula. Anyway, we'll explore these next couple problems sometime later in the week. You guys have a great day. Thank you for tuning in.